Purely mechanical systems face strict physical limits. Without embedded intelligence to monitor stress and adjust to changing conditions, rigid physical mechanisms inevitably reach a threshold where precision fails and adaptability drops to zero. Overcoming these limits requires moving past isolated mechanics. A mechatronic system integrates mechanical engineering with electronics and software. Because these domains interact constantly, they cannot be built in isolation. They demand a concurrent design process from the start. This slide outlines the 5 steps to transform a mechanical design into an integrated mechatronic system. First, engineers add sensors, actuators, and microelectronics. Second, they perform hardware integration, housing these new electronic components within the machine. Third is software integration, implementing the information processing logic. Fourth, the original mechanical system is redesigned to optimize its new digital capabilities. Finally, the 5th step focuses on creating synergetic effects across the entire platform. This final state of synergy is the objective. By fusing these disciplines, the integrated system achieves levels of speed, accuracy, and efficiency that its individual mechanical or electronic parts could never reach alone. When you look at the physical architecture of the final system, every component is governed by one of 2 distinct parallel flows: information or energy. This block diagram maps that architecture. The process begins at the top with the man-machine interface. This interface provides reference variables, the specific target states or goals that a human operator inputs into the system. Following the open arrows, we track the information flow. Sensors measure the current physical state and send that data back to the central information processing unit. The processor calculates adjustments and issues manipulated variables, digital commands directing the system to correct itself. The solid black arrows represent the energy flow. Primary and auxiliary energy supplies route physical power, whether electrical, hydraulic, or thermal, into the mechanical converter and the actuators to ultimately drive the energy consumer. The critical boundary sits on the left side of the diagram. Here, actuators act as the interface, converting the low-power digital logic from the processor into high-power physical energy. On the right, the reciprocal boundary exists. Sensors take the raw physical energy states of the machine and translate them back into digital information for the processor to analyze. Mastering mechatronics requires controlling this dichotomy. Engineers must design systems where highly sensitive, low-power logic can safely and continuously dictate the release of high-power physical forces. Because physical energy and digital information interact unpredictably, engineers rely on rigorous computer-aided tools. CAD, or Computer-Aided Design, handles the geometric modeling, while CAE, Computer-Aided Engineering, simulates how those designs will perform under stress, allowing testing before any parts are manufactured. This computer-aided development happens in 4 stages: drafting constructive specifications, building static and dynamic process models, transforming those models into computer code, and finally, programming the mechatronic software. Engineers use specialized simulation packages like MATLAB, Simulink, and SimPack to handle the computational math. At the core of these software packages are mathematical process models. Engineers obtain these models through 2 distinct paths: theoretical modeling based on the laws of physics, or experimental modeling based on direct observation. The experimental path, also known as identification, requires an existing physical system. Engineers feed inputs into the machine, measure the physical outputs, and use that empirical data to build their behavioral model. The theoretical path relies on first principles. It uses core physics equations to create a unified mathematical language that spans different energy domains, linking electrical circuits, hydraulic fluids, and thermal dynamics into one cohesive model. Theoretical modeling allows an engineer to accurately predict how a single line of C++ code heats up a physical pump, entirely within a digital simulation. Building that theoretical model requires a rigid 6-step procedural checklist. Step 1 is the definition of flows. The engineer identifies the exact type of energy moving through the system, whether mechanical, electrical, or thermal. Step 2 defines the process elements. This maps out exactly where the energy originates at the sources, where it is dissipated at the sinks, and how it moves through storages and transformers. Step 3 is graphical representation. Engineers create block diagrams to track the signal flows and multi-port bond graphs to track the heavy energy flows. Step 4 establishes the equations. This includes balance equations for mass and momentum, and constitutive equations that define the behavior of specific sources and converters. Next, Step 5 applies interconnection equations, using note laws to calculate parallel connections and closed-circuit laws for serial connections. Finally, Step 6 calculates the overall process model, establishing the input and output variables as concrete mathematical transfer functions. A transfer function is an algebraic equation that models how a system's output responds to its input. This mathematical rigor provides the strict parameters required to transition from static design to active simulation. Real-time simulation runs the digital models at the exact speed of physical reality. This is utilized when hardware and software must be developed simultaneously. One major technique is hardware in the loop, or HIL simulation. In an HIL setup, the control system hardware and software are real, physical components, but they are wired into a computer running a simulated version of the physical process and sensors. HIL allows engineers to subject the real controller to extreme laboratory temperatures or simulate failures in the actuators, generating reproducible data without the cost of physical prototypes. The inverse of this technique is called control prototyping. In control prototyping, engineers use an off-the-shelf processor to simulate the control hardware and software, but they connect it to real physical actuators and sensors. Now, both techniques rely on essential illusions. By tricking the digital brain, or the physical body, into thinking the entire system is whole, engineers can safely stress test extreme limits of their designs. Eventually, the design must step out of simulation and into the hardware, where digital logic meets kinetic force. Actuators are devices used to produce physical action or motion. They accept inputs like electrical signals, air, or fluids, and generate physical outputs like linear displacement or velocity. This movement can range from microns to meters. This diagram traces how an actuator achieves power amplification. A low-power control signal enters from the left, modulating a massive supply of unmodulated energy from the top. This intersection triggers power amplification, routing energy through an internal converter to produce the final physical output. The actuator completes the translation. It is the hardware that allows software to physically manipulate a mechanism. This slide categorizes the primary types of actuators: hydraulic, pneumatic, mechanical, and electrical. Regardless of the energy source, they are further classified by their kinematics. They are either linear actuators that push and pull in a straight line, or rotary actuators that generate rotational spin. These devices represent a final, tangible execution of thousands of hours of concurrent engineering and rigorous modeling. Without the actuator, concurrent engineering and theoretical models exist only as static data. Mechatronics is the application of digital intelligence to a physical body.